The picture that we've developed of the atom features a tiny positively charged nucleus containing most of the atom's mass, with the positively charged protons and uncharged neutrons. And then outside the nucleus are the electrons of the atom, and we've seen that some of those electrons are in a tightly bound core that is held close to the nucleus, and some of the electrons are further out from the atom, and these are the valence electrons. So now that we have this picture, we're interested in looking at what happens when two atoms approach one another. And when two atoms get close together, the nuclei never get near each other. They're always far apart. And even the core electrons never really get close together. But the valence electrons are able to interact between one atom and the next. And there are a variety of ways that this can happen. When atoms come together, the valence electrons may stay with the parent atoms, in which case no bonding occurs. And this is something that we typically see with noble gases, where they just hold on to their electrons but don't bond with other atoms. Another thing that can happen when atoms approach each other is that the valence electrons may transfer from one atom to another, and this is called ionic bonding. Valence electrons can also be shared by neighboring atoms. This is called covalent bonding. Or valence electrons can be shared by all of the atoms in a large group, and this occurs in metallic bonding. Now, as the name implies, metallic bonding is observed when a bunch of metal atoms come together. Covalent bonding is observed when nonmetal atoms approach one another. And when a metal atom approaches a nonmetal, that's when you get ionic bonding. And so to develop our understanding of what these valence electrons are doing, it helps to consider two properties of the atom involving valence electrons, and these are the ionization energy and the electron affinity. Ionization energy we've encountered before. This is the energy required to eject an electron out of a neutral atom. So the idea is if you dump a bunch of energy into an atom, you can cause it to eject an electron and leave behind a positively charged ion. And so doing this, we're separating a negatively charged electron from a positively charged ion, so energy needs to go in, and it's rather a lot of energy, although it varies quite a bit. It's in the range of 400 to 2,400 kilojoules per mole. And then electron affinity is kind of the other side of the coin. This is the energy that is released when an additional electron attaches to a neutral atom. So the idea here is that if you've got a neutral atom and a new electron comes in, then energy can be released, and this is the electron affinity. Now, the energy involved with electron affinity tends to be much less than for ionization energy, and partly this is because you've got an electron approaching a neutral atom, and so there's nothing really, from a distance, there's nothing attracting the electron. Now, as the electron gets very close, it begins to feel attraction for the atomic nucleus. At the same time, it's feeling repulsion for the electrons in the original atom. And so, depending on the balance of attractions and repulsions, the energy that's involved is typically small, and it's in the range of negative 170 to positive 350 kilojoules per mole. Now, to give you some context here, for comparison to these energies, the total binding energy of the electrons in a typical small atom like oxygen is 197,000 kilojoules per mole. So compared to the total amount of energy bound up in an atom, these ionization energies and electron affinities are pretty small. But nevertheless, they're very important in understanding the behavior of these atoms. And we can look at that if we make ourselves a graph. If we put the ionization energy of the atoms on the x-axis, if we put the electron affinity on the y-axis, and fill in dots for all of the different elements, this is what we see. And in this graph, the atoms toward the left have a low ionization energy. That means that they weakly hold on to their valence electrons. It's easy to remove a valence electron from those atoms. The dots on the right side of the graph represent atoms that tightly hold their valence electrons. They have a high ionization energy, so it's much more difficult to remove a valence electron. Now, toward the bottom of the graph, we have atoms with very low or negative electron affinities, so they don't attract new electrons. And then dots toward the top of the graph have high electron affinity. Those atoms strongly attract new electrons. And you can see in this graph, most of the elements are sort of clustered in this area where they've got a moderate ionization energy and a fairly small electron affinity, but there are quite a few atoms, quite a few dots on the graph that are outside of here that are sort of spread out in various places. And we can get some more insight into what's going on here if we color code the atoms based on where they are in the periodic table. So if we make the metals yellow, the metalloids purple, and the nonmetals green, this is what we see. And there's a striking pattern here that all of the metals on the periodic table are on the left side of this graph. They all have a relatively low ionization energy, and all of the nonmetals are on the right side of this graph. They all have a relatively high ionization energy. And within each group, there's a wide range of electron affinities. But it's the ionization energy that really determines whether an atom is going to behave as a metal or a nonmetal. Now we can pick out some structure, some additional structure in this graph if we look for some of the groups that we know about in the periodic table. For instance, the alkali metals are over here on the far left of the graph. These are metals that are easily ionized. They tend to be very reactive. On the other side of the periodic table are the noble gases. These are very unreactive, and they form sort of a constellation in the lower right corner of our graph here. The halogens are a set of nonmetals that are very reactive, in contrast to the noble gases, and they appear up at the top of our graph. The chalcogens, oxygen and its congeners, form another cluster in our graph here. The pnictogens, nitrogen and its congeners, are along in here, sort of in the middle-ish. And then the other two nonmetals, hydrogen and carbon, are here right around the middle of the graph. And then the last few metalloids, silicon, germanium, and boron, are over here.